Hello everyone, and welcome to this video on section 3.7 titled Improper Integrals. In this video, I'm going to be taking you through a preview version, a sample version of a Newton-Alta assignment for this section 3.7 on improper integrals. Please understand that the questions I see in this video may not be exactly the same as the questions you see when you work on the assignment yourself. But the objectives will be the same, and so I'm hoping that, watching me do them here will help you in some way when you work on it on your own. All right, so here's the Newton-Alta page. You won't see the word preview up here, but you'll see the title of the assignment in the upper left-hand corner. Upper right-hand corner, you have the mastery bar, which shows you how far along you've gotten. Next to that, you have your activity log, which shows you all the objectives from the assignment. It looks like there are 3 objectives, and you can switch between bold-headed objectives by clicking on Start, and that'll take you to a different objective. If you happen to be really struggling on a particular one, you can move to another. You'll see a current objective. Underneath that, a question related to that current objective. And at the bottom of every question, you should see a feedback button. If you see any typographical errors or problems with the answer explanations, anything at all, you can send feedback directly to Newton and hopefully they can fix things. You will not have this instructor cheat button, right? This is for instructors only. But you will have a more instruction button. So if you're ever struggling with a particular topic, particular objective, try clicking on this and you'll be taken to another area where you'll have some further reading to do or videos to watch or both. And then they'll give you questions related to that reading or videos and you can work through the assignment that way. Okay. So this first objective I'm seeing, evaluate an improper integral over an infinite interval. All right, so what we're going to see with all these improper integrals is that we're going to be able to rewrite them as limits. So instead of integrating over some infinite interval start, I will be integrating over some finite interval and then have one of the limits of integration approach infinity or negative infinity. For example, right, this first question, evaluate the integral. We're given the integral from negative infinity to 7 of x times e to the x dx. Now, since only one of the limits of integration is infinite, I don't need to split it up. We may see later integrals where you're going from negative infinity to positive infinity. If you leave it the way it is, that could cause issues, create situations where you are taking an indeterminate limit. So in those situations, when both limits of integration are infinite, you do need to split up the integral into the sum of 2 integrals where only one of the limits is infinity. But like I said, hopefully we'll get to some examples like that later. And then if the integral is divergent, divergent just simply means the limit is not finite. Divergent means the limit is not finite. Convergent, on the other hand, would mean the limit is finite, and that'll be what our integral converges to, right? We'll find a value. But if the integral is divergent, we'll enter this circle with the slash through it. This is like the empty set symbol, right? Or no solution symbol. Right? Okay, so let me write this out. All right, so we have the integral from negative infinity to positive 7 of x times e to the x dx. All right, so like I said earlier, we're going to turn this into some sort of limiting process. What's going on here is, imagine my integrand is, to imagine this, it is. Let's say this is, some function of x. I'll say f of x equals x times e to the x. And I'm going to be drawing a very, very rough sketch of this. I'm not going to go through the whole derivative and second derivative to look for intervals of increase and decrease and inflection points or anything. I'm just going to draw a very, very, very rough sketch of this function from negative infinity up to, positive 7 here. Now, I would know that, 0, 0 is on the graph of this. And then when x is 7, you'd have 7 times e to the 7th power, right? That'd be a pretty reasonably sized number. And, for all positive values, it would be positive. And then when x is negative, it would be negative. And of course, as x goes to positive infinity, the graph of this thing would be getting gigantic. Again, very rough sketch. I don't even know if it's concave up here. I'd have to do some more work. I just know there's a connection from this point to this point. And then, for negative values of x, this would have a negative value. You'd have a negative times a positive, right? E to any power would be positive, but it's being multiplied by x, so that make it negative for negative values of x. And so it would be negative, below the x-axis. But after a while, if x is going to negative infinity, right, you're going to the left forever, this would be negative infinity times 0. But e to the x, you may recall from maybe calculus 1, this will shrink a lot faster than this will blow up. So we're going back to 0. Okay, so eventually this is coming back down. Again, I don't know exactly where it's concave up, concave down, but I know at some point it's got to come back and approach the x-axis, get thinner and thinner and thinner as you go to the left. So this integral here is actually this net area, right? It's this area, to the x-axis over here, this positive area, along with all of this negative area. So what we're going to do, right, again, I said this at the top of the video, this is this way forever, getting thinner and thinner and thinner. What we're going to do, instead of having, negative infinity be a limit, because, negative infinity is not really a number, it's more of a concept, an idea. I'm going to turn this into some finite interval. So I'm going to pick a value on the x-axis here called, now I like calling it p. You can call it really anything you want. And we'll do this area here from x equals t to 7. Right, this net area. And then to encompass the area in question, this infinitely large interval that we're going over, I'm then going to have t approach negative infinity. Okay, so that's going to turn, again, this integral into a limit. So I'm going to rewrite this now, right? This integral from negative infinity to 7 of x times e to the x as the limit as t approaches negative infinity of the integral from t to 7, right? Again, we're going t to 7, and then having t go to the left more and more, right? Have t approach negative infinity of x times e to the x dx here. All right, so now let's go and integrate this expression, right? Integrate this x times e to the x, which I would do by parts. All right, that is a product of two different kinds of function. So we have our u and our dv. Now u, I would just simply have x be the u and dv be the e to the x dx. Then du would be dx and v would be e to the x, and I'll just skip to the end here. We're going to have this as the limit as t approaches negative infinity of, remember it's the integral of u dv is uv, so x times e to the x minus the integral of v du, but that would be e to the x dx, which is just e to the x again. Okay, and then this is going to be from, x equals t to x equals 7. So I'll plug in 7, plug in t, and I'm also, you know what, I'm going to, just to make the limit later a little easier, I'm going to factor out e to the x from this. You'll see why I'm doing that in a second. This is the same as e to the x times x minus 1. All right, so I'm bringing this down here. This is the limit as t approaches negative infinity of, when I plug in 7, we'd have, e to the 7th times 6. So 6 e to the 7th. That's when I get when I plug in 7 for x, and then minus, when I plug in t, you got e to the t times t minus 1. Okay, and the reason I did this is, yeah, when t approaches negative infinity, right, this expression, e to the t would be e to some big negative number that'd be going to 0, and then this would be going to negative infinity. So you do have an indeterminate. Like I mentioned earlier, the exponential will shrink a lot faster than the linear polynomial will blow up. So this is actually going to 0. Now you can set it up so that you can use L'Hopital's rule or whatever. I'm not going to do that here. I'm just going to say I know this from my calculus 1 experience. So this approaches 0 as t goes to negative infinity. So our limit here is 6 times e to the 7th, right? Which is a finite value, right? That is not infinite. So that means that our integral up here, right, this limit, this integral, this net area as t goes to negative infinity approaches some finite value. And if that is the case, they call this improper integral, convergent. Right? It is convergent, and it converges to 6 e to the 7th. Okay, so what I'm going to do next is show, let's verify this with a calculator. All right, I'm just going to do this for maybe a couple of these examples throughout the video. But I'm going to go to that desmos.com website, free online graphing calculator. And I'm going to enter this integral. Now the nice thing is, you can actually put in infinities or negative infinities as limits. The lower limit, I can just write minus and then type out the word infinity to 7 of, and then x times e to the x dx. And we're seeing that there is, it doesn't say undefined or something, anything like that. It actually has a value, right? Looks like it converges. And this should be what we stated was 6 times e to the 7th power. And look at that, right? They are the same value. Now the problem with this is if it comes back undefined, you got to be careful because it might still converge. It just might converge to a number that the calculator can't handle. All right, so just because something says undefined here doesn't mean it's not convergent. You might have to go actually and test it out. But if you actually enter the improper integral into your Desmos calculator and it comes back with a value, that's telling you it's convergent. All right, and it converges to this 6e to the 7th that we found. So that is what I shall enter back in the assignment, right? So we have 6, e to the 7th power. And notice it doesn't ask you for a rounding answer, right? It doesn't ask you to give an approximation. So yes, this calculator is great to tell me if something converges or not, or it tells you if it converges. Again, if it says undefined, it might converge, but more than likely it diverges. But you're going to have to do a little more if it says undefined. But the thing is, though, they want the exact value it converges to, right? Which is again here 6e to the 7th. Right, submit. Wonderful. And then, of course, after every answer in a Newton Alta assignment, you are given an answer explanation, whether you're right or wrong. And I would highly recommend reading through these, especially if you're wrong, right? Just to see if you can figure out where you went wrong. Even if you're right, take a glance through these. Maybe they do something in a way that you like better and could use for future problems. So yeah, so you see they remind you about L'Hopital's rule here. Like I said, I knew that an exponential times a linear would go to 0. That you could rewrite things so that you can apply L'Hopital's rule like they do here. Okay. So if you want to read through this, totally fine, but this ends up converging. All right, great. All right, so here's another one, very, very similar, where the lower limit is infinite and the upper limit is not. Again, if both were infinite, we'd have to split it up into a sum of two integrals where only one of the limits of integration was infinite. All right, just be careful. All right, so we have the integral from negative infinity to 4 of negative, 5 over x squared plus 16 dx. Okay, and notice enter your answer using exact values in terms of pi, right? So they're predicting that, pi will show up in our answer. Let's see. So here we go. This time I'm not going to draw the region. All right, I'm just going to perform the integration. First, write it as a limit. So we have the integral from negative infinity to 4 of, negative and then 5 over x squared plus 16 and then, dx. Okay. So once again, right, this negative infinity down here, I'm going to replace this with t, and we'll take the limit as t approaches negative infinity, right? So we'll go from t to 4, some finite interval, and then have the t approach negative infinity, right? Make it approach an infinite interval. All right, so again, I'm going to write this as the limit as t approaches negative infinity of the integral from x equals t to x equals 4 of this negative 5 over x squared plus 16. All right, now this integral, I'm going to pull the negative 5 out, and I'm going to ignore the limits for right now. I'll put those back in after doing the integration. 1 over inside now after pulling the negative 5 out, I got 1 over x squared plus 16. Now you may recognize this as some sort of inverse tangent, because it's going to be. I think this is actually going to be 1/4 of the inverse tangent of a quarter x, x over 4. But let me go through and refresh your memory as to how to do a trig sub here. This is x squared plus 4 squared, a sum of squares down here. If I let x be replaced then by 4 tangent theta, right, then dx, right, would be 4 secant squared theta d theta. And if I make these replacements, we'd have -5 times the integral of 4 secant, dx up top is 4 secant squared theta d theta. And then down in the bottom here, we'd have, 16 tangent squared, because that's x squared, right? And then plus 16. And again, maybe you can see it, but if you factor out the 16 down here, this is 16 times tangent squared theta plus 1, which is exactly the same as secant squared, right? Remember, tangent squared theta plus 1 is secant squared. So we have a quarter here, 4 over 16. I'm going to pull that out. So you got -5 quarters times just the integral of 1 d theta, right? Because everything else will be gone. And so that's just -5 quarters theta. And if this was x, right, theta would be the inverse tangent or arctangent of x over 4, right? So like I said earlier, if you recognize that right away, that it's a quarter of the inverse tangent of quarter x, right? You could just jump to that. All right, so we have -5 quarters, times the arctangent or inverse tangent of x over 4. Right. So yeah, now just gotta throw the limits back in here. We're doing t to 4, t to 4, t to 4. Oh, that shouldn't be t to 4 with the thetas here. Sorry, these are values of x. But now that I'm back at x, we get this. We're doing the limit as t approaches -infinity of this -5 quarters times the inverse tangent of x divided by 4 from, x equals t to x equals 4. So we have the limit as t approaches -infinity of plug in 4, plug in t. Now the inverse tangent of, 4 divided by 4 is 1. Inverse tangent of 1, again, I'm assuming you know things about your inverse trig functions from like a pre-calculus class, all right? I'm not doing a whole thing on inverse trig functions here. Inverse tangent of 1 would be pi over 4. So this would be -5 pi over 16. All right, because you have -5/4 times pi over 4 when I plug in 4 here. And then minus, and then -5/4, so plus 5/4. Now the inverse tangent of p over 4. We'll talk about that now. Remember your inverse tangent function, when the input of the inverse tangent function is going to a positive infinity, the output's approaching positive pi over 2. Remember, the inverse tangent has a range from -pi/2 to pi/2. When the input is going to negative infinity, the inverse tangent approaches -pi/2. So that's the limit here, right? T is approaching negative infinity, right? So this input of the inverse tangent will be approaching negative infinity, meaning that this will be approaching -pi/2. So this is -5 pi over 16, and then -5 pi over 8, which is actually 10 pi over 16. Okay, so -5 pi over 16 minus 10 pi over 16 is -15 pi over 16. There's the value of this integral. So again, this is a convergent integral. It actually has a finite limit. And once again, let me test it out. I'll enter this just to double check, that my values are correct here. back on the Desmos calculator, we're going from negative infinity to 4, and my integrand was, negative 5 over x squared plus 16. All right, so you see that after entering this, I'm getting this negative 2.945. It looks like it actually approaches a finite value. Now, what is that value? Hopefully that is what we just stated, negative 15 pi over 16. And look at that, they do match up to at least this many decimal places, so it looked pretty good. So back here, I'm going to enter my negative 15, and the pi symbol should be, it's not showing up here, but if I go to the keyboard to basic, there's pi, right? There's pi. So negative 15 pi, divided by 16. And this should be good. Wonderful. Okay. And again, read through the answer explanations. Moving on. Okay. Yet again, I really hope this doesn't happen to you, but I have another integral where just the lower limit is infinite. And you may see some where just the upper limit is, positive infinity. And once again, I'll remind you, if both are infinite, if it's going from negative infinity to positive infinity, you must split up the integral into the sum of two integrals, from negative infinity to, say, 0, and then from 0 to infinity. Now, it doesn't have to be 0. It can be any finite value you wish, but usually 0 is a good choice. And then you find both those integrals, and if both converge, the whole thing converges to the sum. If one of them diverges, the whole thing diverges. But I'll keep reminding you of that, as so far we're not seeing that. I wish we were. Well, here we go again. I'll write this as a nice limit and see if it actually converges to some value. And again, if the limit's not finite, we'll say it's divergent. All right, so here again we have, integral where the lower limit is negative infinity to, 4 of 3 times e to the negative 3x dx. Now, I do have a feeling, because my values of x here are negative, most of them, right? Negative infinity up to 0, and then you got to 0 to 4, these will be small. But when you plug in bigger and bigger negative numbers, this e to the negative 3x becomes e to a big positive power. So the graph of this, if you go to the left, will be blowing up. It will be getting huge. And the area underneath that will be, I have a feeling this will be divergent, have an infinite limit. But let's go through it. So I got the limit as, again, I'm going to replace negative infinity with t. T approaches negative infinity. And we'll integrate from x equals t to x equals 4, right, of 3 times e to the negative 3x dx. This is a nice simple integral here. The integral of e to the negative 3x would be e to the negative 3x, but then divided by negative 3. So that makes this negative 1 e to the negative 3x, right, when I anti-differentiate. So we have the limit as t approaches negative infinity of negative, e to the negative 3x. And we're going from x equals t to x equals 4. Put in the top, put in the bottom, subtract. We have the limit as t approaches negative infinity of. Now when I plug in 4, this would be negative e to the negative 12th power. Then minus, which will be minus a minus here, so plus. And then e to the negative 3t. Okay, so this is going to be, this is a constant. Negative e to the negative 12th, that's going to stay the way it is. But if t is approaching, negative infinity, this expression then is approaching infinity, and, e to the infinity would be infinity. It is blowing up. This is getting huge. So this particular integral has an infinite limit, meaning that the integral is divergent, right? Not approaching some finite value. All right, so when we go back to the assignment, I'm just going to enter that circle with the slash symbol they told us to enter. All right, now on the calculator, all right, how are you going to suss out that you have a divergent integral here? Well, now if I entered it with the infinity, right, just int for the integral symbol to come up, and then negative infinity for the bottom, and limit and 4 for the upper limit. And then we have 3 times e to the negative 3x power dx. And now, I mentioned this earlier. Just because it says undefined doesn't mean it's divergent. It could be converging to a number that the calculator can't handle. So it'll say undefined. But there's a really good chance that if it says undefined, it's divergent. So what I'm going to do instead is this. All right, so I'm going to call, on the calculator here, I'm going to call bottom limit x and change the variable in here to a dummy variable. Change these to t. I know this is different than what I was doing on paper, but I want to be able to make a table. All right, and the only way to make tables is if your input's x on Desmos. So I want to make a table and have x, just plug in bigger and bigger negative values for x. That way I'll be like approaching negative infinity. So I make a table, and then I'll just start plugging in values of x. Now you notice when x is negative 1, this integral has a value of 20. And when x is negative 2, it's 403, right? It starts getting large quickly. So yeah, I'll just go down here to the 0 row and plug in, say, negative 10. And look at that. I mean, that's gigantic. That's gigantic. 1 times 10 to the 13th power. Huge number. And then negative 100. 1.9 times 10 to the 1/30th. Huge number. So even just at negative 100, you're seeing that the value of this integral is blowing up, right? From negative 100 to 4 for this is huge. So right there, just from the table alone, I'd say, man, this has got to be divergent. And look at the graph too, right? Like I said, the graph of this as x goes to negative infinity. Look at that. Oh, it's going up so quickly, not approaching any finite value at all. So that's a way, if an integral came back undefined, I'd set it up in some way so I could make a table and then see what happens, when I plug in values that approach infinity or negative infinity. Yeah, definitely a divergent integral this time. So remember the symbol for that was this circle with the slash through it they want us to enter. Great. Divergent for sure. Okay. All right, so finally we get one that's a little different. Once again, if you get negative infinity to positive infinity, you must split it up to the sum of two integrals, say one from negative infinity to 0, plus another integral from 0 to infinity. And look at both of them separately. Now, if they both converge, it's convergent. If any one of those diverges, it's divergent. All right, so, and what if they were both convergent? The convergent value would be the sum of what they converge to, right? The integral from negative infinity to 0, whatever that converges to, plus whatever the integral from 0 to infinity converges to. Right? So just be careful, because I feel like this is going to be the last one that I'm seeing And so if you see any from negative infinity to infinity, you gotta split it up. Okay. All right. So we have the integral from 6 to positive infinity of negative x times e to the negative x dx. Now this is pretty similar actually to an integral we saw in the first example of this video. I'm going to do this one by parts really quickly. All right, so let's write this out. I've got the integral from x equals 6 to infinity of negative x times e to the negative x dx. So again, I'm going to write this as a limit. So instead of infinity up here, I'm going to call it t and just have t approach infinity. Pardon me. All right, we have the limit as t approaches infinity of the integral from 6 to t of this, negative x times e to the negative x dx. Once again, I got a little product here of a polynomial and an exponential. So I'll just do a quick integration by parts, right? It's only a linear polynomial, so this should be quick, like in the first example from this video. I'll have u be negative x, and dv be e to the negative x dx, and du be negative 1 dx. V will be negative e to the negative x. And we get our limit as t approaches positive infinity of, and remember the integral of u dv is uv, so it's going to be x times, multiply the u and the v, be positive, x times e to the negative x, minus the integral of v du, but v du would just be, e to the negative x dx. So minus the integral of e to the negative x is minus e to the negative x. So this would be plus e to the negative x. And again, like in the first example today, the first problem in this video, I'm going to factor out e to the negative x here, get an exponential times a polynomial, so that way the limit will be easier to talk about. And you can set up L'Hopital's rule or whatever, set up a situation where you can use L'Hopital's rule. But I'm just, again, going to be taking prior knowledge from Calc 1 and stating the limit right away. So we've gone from x equals 6 to x equals t. So I have the limit as t approaches infinity of, plugging in t, you got e to the negative t times t plus 1 minus, and then I plug in 6, that'd be 7 e to the negative 6th. 7 e to the negative 6th. And once again, this first term here, you'd have infinity times 0. As t goes to infinity, right? This would be e to some big negative number. This would be getting smaller, going to 0. This factor would be going to infinity. So that's indeterminate. And you could write this as t plus 1 over e to the t, and then use L'Hopital's rule, right? The infinity over infinity case. But the exponential is going to shrink a lot faster than the linear is going to blow up. So this is going to 0. All right, and you can again set it up for L'Hopital's rule if you want, but that term would be going to 0. So this ends up being negative 7 times e to the negative 6th power. Convergent, right? That is a finite limit. That is not infinite. All right. And let's test it out again. I'm just going to double check by entering on my calculator. All right, so we had the integral, this time from 6 to, and I'll type in the upper limit as infinity, of negative x times e to the negative x power dx. And we're getting negative, 0 point, a finite value. All right, looks like it's convergent to this finite value here. And hopefully that's the same value as what we stated, right? Negative 7 times e to the negative 6th power. And look at that. Those match to that many decimal places, so it looks pretty good. All right, so back here, typing in negative 7 times e to the negative 6th power, or negative 7 divided by e to the 6th. Same thing. Great. All right, so that finishes that one with the infinite interval objective. Once again, I keep reminding you that, and they say it here in the answer explanations, if you have both limits at infinity, split it up. And if both converge, the thing converges. If either one diverges, then it diverges. All right, they say it diverges. So read through that again. Just keep that in mind, okay, please. Because I didn't see any here, unfortunately. Let's move on, though. Okay, so now we're asked to evaluate an improper integral with an infinite discontinuity, or a discontinuity over the interval of integration. All right, so we're integrating now, instead of over an infinite interval, like from 0 to infinity or negative infinity to 2, it's over a finite interval, right? So from 0 to 2. The problem is the function that is in the integrand is not continuous over that interval. Now, there are three cases here, right? One where it's not continuous at the lower limit, one where it's not continuous at the upper limit, and then one where it's not continuous for some value in between. And analogous to the infinite limits cases, when the function's not continuous for some value in between the upper and lower limit, you gotta split it up, write it as a sum. All right, and I'll point that out again. I'm sure they'll point that out in the answer explanations as well again. All right, so I'm going to write this integral out here. So this integral, we have the integral from x equals 0 to of x to the 4th times the natural log of 2x. And then, of course, with respect to x, right, times dx there. All right, so like I said, this x to the 4th, times the natural log of 2x, the integrand, I'll draw a picture of this. Again, a very, very rough picture. I'm not doing first derivative, second derivative, or I'm not finding where it's concave up, concave down, any of that junk. I'm just going to draw a very, very rough sketch of this function. And maybe we'll take a look at it in Desmos later for a better picture. But think of this as some function, right? F of x equals x to the 4th times the natural log of 2x. And I'm going to graph this, over the interval from 0 to 2. And very rough. So from x equals 0 to x equals 2, I'll put 1 in here as well. Now, this function, at 2, you'd have 16 times the natural log of 4, whatever that is. Or 32 times the natural log of 2, something like that, right? Properties of logs. At 1, you'd have 1 times the natural log of 2, which would definitely be smaller. Just the natural log of 2, which is about 0.69 something, right? But you'd have natural log of 2. But then, I guess I could put a half in here because that would give me 0. Because the natural, you'd have 1/16 times the natural log of 1 when x is a half, but that would be 0. And you see it's decreasing. And what's happening is, as you approach 0 from the right, remember the natural log of something positive and small, right? If x approaches 0 from the right, this 2x will be positive and tiny. And the natural log of something positive and tiny is a big negative number. Remember the log function approaches negative infinity as x approaches 0 from the right. And x to the 4th will also be, this will also be positive and tiny. All right, so this would be approaching 0. This would be approaching negative infinity. Perhaps I should set this up for L'Hopital's rule, right? Because again, as x approaches 0 from the right, this x to the fourth times the natural log of 2x, this is approaching 0 times, and this is approaching negative infinity, which is indeterminate. And I'm not as good with my logs here as I am with the exponentials, because I know logs grow more slowly than uh, power functions. So this should be all right. So let's rewrite this as, say, natural log of 2x divided by, and then x to the negative fourth. Right, that'd be the same thing as times x to the fourth. Now we have this approaching negative infinity as x approaches 0 from the right. And this would be approaching positive infinity because this would be 1 over x to the fourth, right? 1 over something small, which would be something huge. And now I can apply L'Hopital's rule, taking the derivative of each of these with respect to x. So you'd have, 1 over 2x in the numerator and negative 4 over x to the fifth in the denominator. And I multiply by the reciprocal here. Okay, so this would end up being negative x to the fifth over negative x to the fourth, negative 2x to the fourth. No. Negative 1/8 times x to the fourth, right? Yeah, sorry, because you'd have 1/2, and then this becomes x to the fifth over 4. The 4 is in the denominator. So negative 1/8 x to the fourth. And this would approach 0, actually. All right, so this actually approaches 0. So what's going to happen here is, for values between 1/2 and 0, we're going to approach the origin, right? But it's not going to be there, though, because you can't take the natural log of 0. That's undefined. So the graph's going to do something like this in this interval, right? And approach the origin. All right, let me, just to double check my work here, I'm going to pull up Desmos and see what the graph of this function actually looks like between 0 and 2. There's 0 to 2 here. So, f of x equals, or y equals x to the fourth, not percent, x to the fourth times the natural log of 2x. And yeah, see, add a half, you get to the negative side, and then you see how it comes back up, right? When x equals a half, it crosses the x-axis 0. Oh, I'm not on my, sorry, I'm so sorry. All right, so here we are. So again, I'm looking at, all right, so I punched in y equals, or f of x equals x to the fourth times the natural log of 2x. And we're looking at, from 0 to 2, this graph here. And like I said, you see at x equals a half, right? It crosses the x-axis and becomes negative, and then it starts sloping back upwards towards the origin, but the origin is not there, right? There's a hole, see, 0 undefined. So yeah, very similar to the graph I have by hand here. Again, not perfect, but it's very similar. It should be actually concave up here, not concave down, but whatever. So this integral in question is actually this area here. Right? Now it looks to me, okay, it looks to me like this is going to converge, right? This is just a missing point. This isn't some off to infinity thing. So I feel like we can get this area and get that area, and then this will be positive area, this will be negative area, and then they'll add up to something finite. I have a feeling based on the look of this that we'll have a convergent integral. But again, I can't use 0. Right? I can't use 0. This function, this integrand, is not defined at 0. So, like with the improper integrals with an infinite interval, I am going to instead turn this, into some limiting process, right? So instead of going from 0 to 2, because again, I can't use 0, I'm going to go from x equals t, like I used before. X equals t to 2, right? Find this area, this net area, and then have t approach 0 from the right, right? Have t approach 0 from the right side, right? The little 0 plus. And we'll see later, if the function is not continuous at the upper limit, we'll have our t approach that value from the left, right? The little minus. But here it's approaching 0 from the right. And the closer t gets to 0, right, the closer our area will be to this area they're looking for, this integral they're looking for. All right, so I'm going to write that on the next page here. So what we have now is this integral we were given is the limit as, I'm going to replace 0 with t and have t approach 0, from the right. So we're plugging in little tiny positive values for t. For the integral from t to 2 of x to the fourth, times the natural log of 2x. Okay, this is another one of those I would use integration by parts on. All right, you got a polynomial times a log, right? Two different kinds of functions being multiplied. Great candidate for integration by parts. And this time I'll have u be the log, right? U is the natural log of 2x, and then dv is the rest of it, right? X to the fourth dx. Then du would be 1 over 2x, times 2, and then times dx. So really just 1 over x dx. And then v would be 1/5 x to the fifth, right? And so we have, 1/5 x to the fifth times the natural log of 2x, right? And then minus the integral of v du. We pull this 1/5 out, and then we have the integral of x to the fourth, right? X to the fifth times 1 over x, so x to the fourth dx, and that's 1/5 x to the fifth again. This will be 1/25 x to the fifth. Okay, so we've got this. We got the limit as t approaches 0 from the right of, 1/5 x to the fifth times the natural log of 2x, and then minus, 1/25 x to the fifth. Okay, and we're going from x equals p on the bottom to 2 on the top, right? X equals 2. So I plug in 2, plug in t, and we'll subtract. So we have the limit as t approaches 0 from the right of the following. Now, when I plug in 2, 2 to the fifth is, 32. So we got 32 fifths times the natural log of 4, right? 2 times 2, minus 32 25ths. Okay, so there's the value at 2. Put in parentheses, that's the value at 2. Minus, and then the value at t would be, 1/5 t to the fifth times the natural log of 2t minus 1/25 t to the fifth. All right, we're going to have t approach 0 from the right. Now, based on the work I did earlier with L'Hopital's rule, right, when we had x to the fourth times the natural log of 2x, that approached 0. Well, this is t to the fifth. That's going to go to 0 even faster than x to the fourth. So this will be approaching 0. Again, you can set up a L'Hopital's rule thing again like I did earlier. This would also be approaching 0. So you have 0 minus 0 here, right? So this whole expression after the minus sign here is approaching 0 as t approaches 0 from the right. So we do have a finite limit, and it's this thing here. Right? It's 32 fifths times the natural log of 4 minus 32 25ths. Right? That would be the net area that I drew earlier, right? This area here. right? But again, this is considered positive area, that's considered negative area, but they add up to this. We do have a convergent integral, which I suspected from the beginning, right? That the area didn't look like it was getting crazy huge or anything. Looked like a nice finite area. And then let's double check it, right? Like I've been doing. So back to my calculator here. Let's enter that integral we started with, right? We have the integral from 0 to, and then it was, x to the fourth times the natural log of 2x dx, and I'm seeing a nice finite value here, right? It doesn't say undefined. Once again, if it says undefined, it might still be convergent. You might have to do something else. But there's a good chance it's divergent if it says undefined. But then I would go about and make a table and stuff. Let's see if that's the same as the value we got. We had 32 fifths times the natural log of 4 minus 32 25ths. And yes, these do match to at least that many decimal places. So probably the value this is converging to. Great, and that's what I'll enter in the assignment. 32 fifths, natural log of 4, and then minus 32 25ths. Wonderful. All right, and again, read through see again, they go over the different cases and the answer explanations, right? So we saw this case where it was the second case here where the function's not continuous at the lower limit. So I had t approach that limit from the right. If it's at the upper limit, I'm going to have t approach that value from the left. And I mentioned this third case, right? So just in case I don't see any problems like this, if it's continuous at every value except for some value in between the ends, right? Then you break it up, split it up to a sum, go from A to that value, and then from that value to B, and then you're doing, limit as t approaches this value from the left for the first integral, limit as t approaches this value from the right for the second integral. And if both of these converge, they'll say the original integral is convergent. If at least one of these diverges, they'll say it diverges. Right? So and be careful. And you're not continuous at some value in between, right? You got to split it up. Just like earlier when we had both limits at infinity, right? From negative infinity to a positive infinity, you got to split it up as a sum. All right. So moving on. Ah, beautiful. This is one of those integrals. I have the integral from 2 to 7 of this 4 over x minus 3 cubed dx. This function, 4 over x minus 3 cubed, would not be continuous at 3. And 3 is between 2 and 7. So this is actually one of those that I was talking about where we have to split it up. So I'm finally seeing one of these examples. So I'll go in my paper and I'm actually going to draw a picture of this one because the last problem didn't have an infinite discontinuity. The graph approached the origin; it didn't go up forever or down forever at the discontinuity, but this one will. So from x equals 2 to 7 of 4 over x minus 3 cubed dx, and I will draw again a rough sketch of this function. Call it f of x again. This 4 over x minus 3 cubed, and look at a really rough sketch of this from x equals 2 to 7. Again, there's going to be a discontinuity in between here at 3, right? X can't be 3, you'd be dividing by 0. And I know from prior experience that this will be one of those infinite discontinuities. You're going to have a vertical asymptote. Now when x is 2, you'd have, negative 4 as your output. 2 minus 1 is negative 1. 2 minus 3 is negative 1. Cubed would be negative 1 still, right? So you'd have an output of negative 4. 2, negative 4. And as I approach 3 from the left, values less than 3, this would be getting closer to 0, but negative. So I'd have a negative number, and it's to an odd power, so still negative. I'd have a negative tiny number. Some positive 4 divided by a negative tiny number would be a large negative number, right? Going to negative infinity on the left side of 3 there. And then 7, 7 minus 3 is 4. 4 over 4 cubed would be 1 over 4 squared would be 1/64th. Or sorry, 1/16th. 1/16th. It would be 4 over 64. 1/16th. So 7 1/16th. And then as you approach 3 from the right, it'd be a little bigger than 3. This would be getting close to 0 in the denominator, but positively on the positive end. So you'd have 4 divided by some tiny positive number. That would be blowing up to positive infinity, right? Dividing by a tiny positive is the same as multiplying by a large positive. And so this integral is actually about finding this net area. The area down here, but it goes down forever, right? It's getting thinner and thinner and thinner between this and the asymptote, but it's still going down forever. And so I have like almost like an infinite situation, like in the first objective for this assignment. And then same thing up here, right? I'm finding this area, but it's getting thinner and thinner and thinner, but it's going up, forever, forever that way, forever that way, So I gotta write these as limits, and we got to break it up around 3. So like I was saying earlier, right? Now this case where you're not continuous between, I'm going to write this as the integral from 2 to 3 of the function, right? From 2 to 3, where it's discontinuous, of 4 over x minus 3 squared, or sorry, cubed, and then dx. And then add to that this other, this positive area from 3 to 7, and splitting it up at the value where it's discontinuous of 4 over, x minus 3 cubed dx. All right, so I'm going to we'll do these one at a time. All right, so I'm going to call this first integral, integral number 1, maybe I1. And then this second integral, all right, from 3 to 7, I'll call that I2. All right. And like we did with the previous examples, right, I'm not going to go from 2 to 3 because I can't plug in 3. So for this first integral where I'm going from 2 to 3, I'm going to instead go from 2 to t, right, get this finite area here, and then have t approach 3 from the left. All right, so we'll start off doing that. All right, so for that first integral, and again, I'm calling it I1, integral number 1, I'm going to have the limit as, t approaches 3 from the left. Limit is t approaches 3 from the left of the integral, and I'm replacing 3 with t here from the integral from 2 to t of, 4 over x minus 3 cubed dx. So that's going to be the limit as t approaches 3 from the left of, now this should be an easy integral. This is x minus 3, a linear to the negative third power. So you'd have x minus 3 to the negative second, times negative half, which times 4 would be negative 2. This is negative 2 times, x minus 3 to the negative 2, or negative 2, over x minus, or, negative 2 over x minus 3 squared, right? That would be your antiderivative, and then we're going from x equals 2 to x equals t, and having t approach 3 from the left. Well, that would be the limit as t approaches 3 from the left of, plugging in t here, and you've got negative t, or sorry, negative 2 over t minus 3 squared, and then minus, but it'll be minus a negative, so plus, and then when x is 2, 2 minus 3 is negative 1, squared is positive 1. This would be just negative 2, so plus 2. All right. Now, as t approaches 3 from the left, this denominator here would be going to 0, right? And it'd be doing 0 positively, because, I mean, yeah, this would be negative number, some negative small number, but it's being squared. So it's going to 0 positively. And then I have a negative number up top divided by a small positive number. That's the same as a negative times a large positive. So this is going to positive infinity, and then plus 2. This is infinite. This is divergent. And so I don't need to check I2, all right, my integral 2. Because again, if you split it up, the only way they're going to consider the integral convergent is if both converge. And then what it converges to would be the sum of what they converge to, right? You add them up. If either one diverges, they'll say that this is a divergent integral, right? I'll just put div for divergent, all right? So yeah, this was divergent. I don't need to check that one. So even if this converged, it wouldn't matter, all right? If either one of them diverges, the whole thing diverges, right? And I'm not going to check this time. I feel pretty good. The integral diverges. Submit, right? And again, they read through it, and again, they talk about the 3 different cases, right? Just like with the infinite interval objective, right? They, in all these answer explanations, they go over the 3 different cases. And yeah, you see, they did the integral from 2 to 3 again, said it diverges, right? So you don't need to check from 3 to 7. Right? You just know they say the whole thing diverges as long as one of those diverges. All right. Okay. So now we've got the integral from negative pi over 2 to negative 3 pi over 8 of the tangent of 4x times the secant of 4x dx. All right. Let me write that out and try to figure out where the function, the integrand, is discontinuous over this interval from negative pi over 2 to negative 3 pi over 8. The tangent of 4x times the secant of 4x dx. Now, if you don't like having, just 4x in here, maybe you'd rather have just t or u. I'll make a little u substitution. All right, you don't have to do this. And I'm also going to change the limits. Why not? And then du would be 4 dx, right? So this dx would be 1/4 du. So now we have the integral, and I'll pull that quarter out. And then this is secant u, I'm going to write it this way, so maybe it's more familiar to you from Calc 1, right? Secant u, tangent u, instead of tangent secant, and then du. Now the limits, I can also change, right? When you make substitutions, you can change the limits. Now the lower limit, the original was, x equals negative pi over 2, and x equals negative 3 pi over 8 was the original upper limit. Well, if I had x be negative pi over 2, then u would be, 4 times negative pi over 2. So negative 4 pi over 2 or negative 2 pi. Right, that's the value of u. U equals negative 2 pi. And the new upper limit right? The original was negative 3 pi over 8. U is 4 times that, right? So negative 12 pi over 8, which is negative 3 pi over 2. Right? Negative 3 pi over 2 for U for the upper limit. Okay, so now that I got it like this, let's think of like what are values of U that would make these undefined, right? Where are these where's this function, are either of these functions discontinuous? Well, remember, secant is 1 over cosine, tangent sine over cosine, so both of these would have cosines, right, in the denominator. And cosine is 0 at those odd multiples of pi over 2, so we're discontinuous this value, right? There's that value is where the discontinuity is going to be. And there's negative 3 pi over 2, and then this is negative 4 pi over 2, so there's no other ones in between, right? So we got this case where the function in question is discontinuous just at the upper value. So like all the others, I'm going to replace that with t, and we're going to have t approach this, from the left, right? Because we'd be on the left side of that. On the bottom one, I approach from the right, from below, from above, and we're approaching this one from below, so from the left. All right, so this is 1/4 times, and then I'm going to rewrite that integral as the limit as t approaches, negative 3 pi over 2, but from the left, right? So a little minus there from below. The integral from negative 2 pi to t of secant u tangent u du. Now this should be a familiar derivative, right? The derivative of secant was secant tangent. So this is simply 1/4 times the limit as t approaches negative 3 pi over 2, from the left, from below, of the secant of u, and we're going from u equals negative 2 pi up to u equals t. So this is 1/4 times the limit as t approaches negative 3 pi over 2 from the left or from below of the secant of t. I'm replacing u with t and u with negative 2 pi. The secant of t minus, now negative 2 pi is coterminal with positive 2 pi, right? And the cosine of 2 pi was 1. So the secant of this is also 1, right? So minus 1 when I plug in negative 2 pi for u. Okay, now your secant functions, right? Remember the secant function is these, looks like u up, u down, u up, u down, right? Like that with a bunch of asymptotes all over the place. As we approach either of these asymptotes, this thing's going to infinity. Now, negative 3 pi over 2, if you approach negative 3 pi over 2, that's coterminal with pi over 2. But, so negative would be, going counterclockwise, or going clockwise, sorry, clockwise, for a negative angle. There's negative 3 pi over 2. And then, between negative that and pi. So we'd be over here in the first quadrant because negative 2 pi would be all the way around, and we're just below negative 3 pi over 2 right on the inputs. So we'd be in the first quadrant somewhere close to this. So we're going to positive infinity here. So this is another infinite limit. Okay, this is another infinite limit. So this is another divergent integral. All right, has no finite limit, no finite value. And you can test that with the calculator stuff if you want, but I'm just going to enter the, go to the sets here. Put in the little circle with the slash symbol for divergent. Wonderful. And again, they run you through Now they don't do a u substitution in the beginning because again, you don't have to. I just don't like having 4x and 4x inside. I'd rather have u or something, right? Just a simple letter. You didn't have to though. It was simply a quarter. I think the u sub actually caused more writing than was really necessary, but still, you end up seeing the limit is infinite. All right. Now here's another one where the function's not continuous at the upper limit. So I'm going to replace that upper limit with t and have t approach it from below or from the left. So this integral, we have the integral from -4 to 6 of 1 over the square root of 6 minus x dx. So like I said, this function is clearly not continuous at 6, right? That would make me divide by 0. So I'm going to replace 6 with t, and we'll take the limit as t approaches 6 from below, right? T approaches 6 from the left of the integral from -4 to t of, and I'm going to rewrite this as 6 minus x to the -½ power. All right, that's because that's 6 minus x to the half, and it's 1 over that, right? And it's a simple linear to a power. Got to worry about the coefficient of -1 here in a second, but so this becomes, 6 minus x to the half, then times 2, but then also divided by -1, so times -2. So we got the limit as t approaches 6 from the left. That value is a little less than 6 of, and yeah, this was -2 times 6 minus x to the half. -2 times the square root of 6 minus x. Right, 6 minus x to the positive half. Right. And we're going from x equals -4 up to x equals t. Pop those in. So the limit as t approaches 6 from below, so from the left. Now when I plug in t, this is, -2 times the square root of 6 minus t. And that's nice. When t approaches 6 here, this is going to be 0. That's going to approach 0. Then minus, and you got minus and negative, so plus. And then when x is -4, this becomes the square root of 10, so 2 times the square root of 10. And yeah, like I said a second ago, this first term here is going to approach 0 if t is approaching 6 from below. And it's got to approach 6 from below, because if it approaches 6 from above, we'd be taking square roots of negatives and they'd be imaginary, blah, blah. Don't want those, right? So yeah, that limit's 0. And then plus this constant. So we do have finally here, after a few examples, a convergent integral. Right? This is a finite limit approaching a value of 2 times the square root of 10. And you can check with the Desmos calculator, but I'm going to just trust myself now. Right? So 2 times the square root of 10 is what this converges to. Great. Wonderful. All right, so we got the improper integrals with we've done over infinite intervals. We've seen over finite intervals, but where there's a discontinuity. The last objective will be some sort of comparison. Right? We'll do comparisons to determine if an integral is convergent or not. So use the comparison theorem to determine whether an improper integral is convergent. Again, your options here are going to be the integral converges, diverges, or inconclusive. All right, so before I get to this example, let me describe what this comparison theorem is stating for these. These are for integrals over some infinite interval. So comparison. And this is over some infinite interval. All right, so say I have functions over some interval from a to infinity, and they're functions of positive values, right? Positive valued functions. So say here's a function called f from a to infinity, right? Going out that way forever. And suppose function f is, shrinking to nothing, and so is this other function called g that's always above it, or at least as high. So maybe g is doing this, but it's always a little, it's above f. There's g. Now the integral from a to infinity of f, right, would be this area here, right? This area going to the right forever and getting thinner and thinner. And then the area under g would be this area here, which is bigger. It's taller. So again, suppose we have this. So f, we have some function. Again, they're all non-negative. Okay, we're talking about non-negative valued functions. So nothing below the x-axis. So if this is happening on the interval, so if, right, if on the interval from a to, positive infinity, 1, sorry, I forgot to write this. Now 1, if the smaller area, all right, if the smaller area, the area under f, diverges, then the larger one must diverge. If that has an infinite limit, the larger one must be infinite as well because it's even bigger. So if, the integral from a to infinity under f, right, if the area under f diverges, then so does the bigger one, right? Then the integral from a to infinity of g must also diverge. All right, so that's one thing we can tell from this. 2, if the larger one, right, the area under g converges, then the smaller one, being smaller, must also converge to a value that's at, at most the area under g, right? So you got the area under g is convergent, then the area under f must also be convergent to some value that's, either the same as the area under g or less, but it'll be convergent. Right? So if the area under the larger function, g, if that converges, then the area under the smaller function, the lower function, must also converge. All right. Now, there's also the option of, inconclusive, where you can't really tell anything, right? We know if the smaller one diverges, the larger one's got to diverge. We know if the larger one converges, the smaller one's got to converge. Well, what if the larger one diverges, right? If the integral from a to infinity of, the larger one, if you know that that's divergent, then you can't tell what's happening with f right away by comparison. If that diverges, if the larger one diverges, the smaller one could be small enough where it converges, but it could also be big enough to diverge, right? You can't tell. Right? Then you can't say anything about the integral on the area under the smaller one, under f. And you can't say anything. You can't conclude anything, right? It's inconclusive. You can't say anything about this integral under f, right? The area under f. So they're going to say, it's inconclusive. And also, right, if you know the area under f, right, if you know the area under the smaller curve converges, that says nothing about the larger one. So if the area under f is, if you know that converges, the larger one, it may be so much larger that it diverges, but it may be just barely larger and it'll still converge. You don't know. Right, so there's also there's another case where you have an inconclusive case. If the integral under the smaller function converges, then again, inconclusive. All right, I'll just write inconclusive. You can't say anything about the area under G, is all I'm saying. All right, just say inconclusive. All right, so again, those are the scenarios here when we're talking about comparing functions over some infinite interval. All right, so you'll have a smaller one, a larger one, and if the smaller one diverges, the larger one diverges. If the larger one converges, the smaller one converges. Now, if the smaller one converges, you can't say anything about the larger one. You don't know. And if the larger one diverges, you can't say anything about the smaller one. You don't know. All right. So those are what we're dealing with when we're talking about this comparison theorem. Now, the problem I'm looking at, we start off with this integral from 2 to infinity of, 2 plus e to the 2x and then, sorry, e to the negative 2x in the numerator divided by, and then the square root of x plus 7 in the denominator. With respect to x, of course. Now, they're saying compare because this is not a nice integral. You may recall from the very beginning of this chapter, the chapter 3 material, it was brought up that there are some integrals out there that are, they're written in terms of elementary functions, right? Your polynomials, roots, polynomials, radicals, exponentials, logs, rationals, trigs, inverse trigs, right? Your pre-calc functions, right? They're written in terms of those functions, but the expression that they're equivalent to, right, the integral, is not elementary. Or it's just really, really difficult to do. So like this integral here would be either impossible to do with elementary functions or just incredibly difficult. So in those cases, right, this is really difficult, we'll compare it to an integral of a function that's easier to take. So they're doing the integral from 2 to infinity of, now see what they're doing here is they're getting rid of this term and also changing the 2 to a 1. Now we got to determine which one's larger, which one's smaller, but that shouldn't be too hard to do. They're saying compare it to this integral, 1 over the square root of x plus 7. Now, on this interval, we're on the interval from 2 to infinity, meaning that x is greater than or equal to 2, right? The value of x is greater than or equal to 2. 2 plus e to the negative 2x over the square root of x plus 7. if I get rid of this, this term is positive up here, right? E to the negative 2x, that's a positive number. No matter what real number you plug in for x, right? E to any power is positive. If I get rid of that, that'll make the numerator smaller, right? And when you make a numerator smaller, you make a number smaller, right? So this should be less than or equal to, 2 over the square root of x plus 7, which again, if I want to make it this, again, if you make the numerator smaller, if I turn 2 into 1, it's going to make the fraction, smaller, I'm sorry. It makes it smaller. My apologies. Yeah, it's going to make it smaller, meaning my original fraction was bigger, right? So the original fraction here is greater than or equal to this fraction. And then again, I'm going to take this fraction here and turn the 2 into a 1, so we get the function they want us to compare to. And when you make the numerator smaller, you make the fraction smaller. So this fraction should be bigger, right, than 1 over the square root of x plus 7. Again, my apologies for the direction there. All right, so that means the function we were given, that's the larger one than the function they're asking us to compare to. All right, so here's what's happening, right? I'm going to call this, g of x, right? Like on the previous page when I was talking about the comparison theorem, right? The larger one was called g. This is f. And you could draw a very, very simple sketch here, right? We're going from 2 onward. So if something's happening like this, there's g getting smaller and smaller to 0, and here's f underneath it, right? Getting smaller and smaller. Uh, in fact, why don't we take a look at these in Desmos just to get a better idea as to how this is larger than this for values, greater than or equal to 2. All right, so I was calling that one g, the one we were originally given. So we had 2 plus e to the negative 2x power in the numerator, and the square root of x, plus 7 in the denominator, right? And let me put this out of it. There's the graph right now. I just want to look at it from 2 onward. So you see it's definitely, shrinking down to 0, right? It's getting thinner and thinner. You go out here and you see it's getting closer to the x-axis as you move to the right. And then the other function, right, I was calling f, right? This should be the smaller function after x equals 2, 1 over the square root of x, and then plus 7 in the denominator. You see how it's lower? Right, the blue one was my original, the green one's lower than that. Especially, definitely since, x equals 2, all right? All right, so what I'm going to do now is find this integral. If this integral diverges, all right, remember, if the smaller one diverges, the smaller area, the area under f here, if that diverges, then I know the larger one does. I know our integral here diverges as well. Now, if this converges, I can't say anything about the larger one, right? Because the larger one might be just barely bigger and converge, but it also might be a lot bigger and diverge, right? So I'm going to take this integral. We're going to see if it converges or diverges. Again, if it diverges, great. Then we can say the larger one will diverge as well. If it converges, we don't know about the larger one. All right, we'll just say it's inconclusive. So let's bring this up on the next page. We got the integral from 2 to infinity, 1 over the square root of x plus 7 dx here. All right. Okay. So again, am I right? This is a limit. Limit is t approaches infinity. the integral from 2 to t of 1 over the square root of x plus 7 dx. Now for this integral, I'm going to do some substitutions here. So I'm just going to take this off to the side and work with it without the limits for right now. So yeah, having this square root of x down here, not a big fan of that. So I'm going to replace x with u squared. In other words, I'm going to have u be square root of x. Actually, maybe I'll just have it be. Well, let's see what happens when I do this. All right, so then dx, okay, will be 2u du. Okay, yeah, this won't be so bad. All right, so I make these replacements. All right, so dx is now 2u du when x is u squared. And then down here, this is just u plus 7. And I have one of them rational expressions, so I do division. So when I divide, 2u by, it's one of the rational expressions where you have an improper fraction. Right, degree of the numerator is not smaller than the degree of the denominator. Now, when I divide these, you got, 2u divided by u is 2, and then this gives me 2u plus 14, subtract all that. And then this will give me negative 14 for the remainder, right? So this is the integral of 2 minus, and then 14 over u plus 7 du. So this is 2u minus 14 times the natural log of the absolute value of u plus 7. And then I'll go back, and what was u? U was the square root of x, right? So this is the limit as t approaches infinity of, 2 times the square root of x minus 14 times the natural log of the absolute value of the square root of x plus 7. And we're going from x equals 2 to x equals t. Right. So let's put that in. So we have the limit as t approaches infinity of, you got 2 times the square root of t minus 14 times the natural log of the square root of t plus 7. Right, that's when x equals t, and then minus, and then when x equals 2, this is just 2 times the square root of 2 minus 14 times the natural log of the square root of 2 plus 7. All right, and that doesn't need absolute values, that's a positive number. All right. All right, so a lot of stuff to work out here. Now this here, if t goes to infinity, this is actually going to give me infinity minus infinity, which is indeterminate. Right, the natural log of a bigger number would get bigger, and the square root of a bigger number gets bigger, right? And this is one of them indeterminate limits, right? That's bad. So I got to write this some other way. Now, I do know that power functions get larger faster than your logarithms, right? Even if it is t to the half power. But a way I can see how to write this, I can write this as 2 times, and then the natural square root of t I can write as the natural log of e to the square root of t power, and then we have minus, and then I'll put the 14 in here, natural log of the square root of t plus 7 to the 14th power. And this would be this to the second power, so I'd have e to the, and then put these together with the natural log minus natural log, right? Now e to the square root of t to the second would be e to the 2 square root of t. And putting these together gives me natural log of a fraction, e to the 2 root t over just the square root of t plus 7 to the 14th power. So this is like having some exponential over a polynomial in the square root of t. So this is going to get large. The numerator is going to get larger a lot faster than the denominator will. So this is an infinite limit, meaning this is an infinite limit. Okay, you could do you could take a look at this here and do L'Hopital's rule a bunch, or you'll eventually see you'd eventually see that, again, if I replace the square root of t here with x, right, you'd have an exponential over a polynomial, and exponentials grow a lot faster than any power polynomial does. So this is going to infinity, and the natural log of infinity would be blowing up to infinity, right? So this is a case where we have an infinite limit. So this is divergent, right? So that means, right, this was this integral here, which was the area under the small thing, right, under our f. So the area under the smaller function is divergent, right, infinite limit. So the larger one must also diverge as well by comparison, right? So that initial integral I was given, all right, this must be divergent as well, right, by the comparison theorem. All right, so back to the assignment, all I'm going to enter here is diverges, and wonderful. Okay. And again, they read through the answer explanations, they discuss the comparison theorem, and all that. Wonderful. All right, so more comparison theorem. Now look, they give us some graphs here. So here it's on the graph below. We have 3 functions. F, 6 over x squared, which is this upper function, right? If you look at this, that's the top function. G is 2 over x squared plus 2. G is the red one here. That's in between F and H, right? The red is in between the purple and blue, or the black and blue. H of x is e to the negative 3x, and that's this light blue one coming down here. That's the lowest function on the interval from 3 to infinity. So from 3 onward, right, from x equals 3 onward, f is above g and g is above h. It looks like, right, forever. And they're telling us that here, right? F is above g, g is above h, right? G is between h and f, whatever. Now, they're telling you, and you could easily find this, but they're telling us, we know that the integral from 3 to infinity of f, right, the larger function, converges. So then which of the following statements are true? Well, 6 over x squared, that's f, right? That's the top function. So from 3 to infinity, that area under the largest function converges. So the ones under the smaller ones must converge as well, right? They're smaller. They got to converge as well. That's your comparison. So the integral from 3 to infinity of g would converge. The integral from 3 to infinity of h would converge. So we know this. From 3 to infinity of g converges. From 3 to infinity of h converges, right? That's the last option here. Sorry. We know that both of those would converge because they are smaller functions than f, and f converged as well. And again, read through, they discuss the comparison theorem again. Great. So that was nice. You didn't have to do any integration there. Okay, so another one like the first example from this objective. So they're, they're asking us to compare this integral to this one, a much simpler one. Determine whether the original integral converges or diverges, or if it's inconclusive, right, by the comparison test. All right, so once again, I'm going to look at these and we got to determine, which of these integrands is actually the larger function here, which one's the smaller function over the interval from 1 to infinity. All right, so let's do that. All right, so here's the initial integral we're given. 1 to infinity of, you got the natural log of x plus 5 over, and then the cube root of x plus 5. All right, and they're asking us to compare to this integral. So same interval, 1 to infinity, of just 1 over the cube root of x, and then plus 5, right, with respect to x. Now, pretty much like earlier, right, x is greater than or equal to 1 here. And for those values, right, if you start with the original, natural log of x plus 5, and then divided by, and, cube root of x plus 5. If I'm trying to make this, compare this to this function here, the 1 over cube root of x plus 5, right, this natural log of x, when x is greater than or equal to 1, this is greater than or equal to 0. This is non-negative. So if I get rid of this, it's going to make the fraction smaller. So this fraction should be greater than or equal to just 5 over the cube root of x plus 5. And then if I turn 5 into 1 here, 5 is bigger than 1, so this fraction will be bigger than 1 over the cube root of x plus 5, right? So again, the larger function here, which I'll call g, is our original integrand, and the smaller function, which I'll call f, is the integrand of the thing we're supposed to be comparing to. All right, so now let's look at this integral of the small. Now again, if the area under the smaller function converges, we can't say anything about the larger one. If this diverges, then we know the larger one diverges, right? So those are the two scenarios we're looking at here. So this time, instead of actually going through the integral, I'm going to go to the calculator. All right, I'm going to use a calculator here to tell me if this converges or diverges, to help me out here, give me an idea. So I'm going to Desmos here. I'm going to enter this integral. This is just to save some time here, right? Integral from 1. Now let's see if anything happens when I put in infinity. If nothing, if it comes back undefined, I'm going to have to do a table. So 1 over, now it's the cube root of x. So I'm just going to put x to the 1/3 power, right? That's cube root. And then plus 5. And then you get your dx. Yeah, so it says undefined. It says undefined. So I feel like it's probably divergent, but I really want to make sure, so I'm going to make a table. So I'm going to call this infinity x and change my variable in here to a dummy variable, call it maybe t or something, t to the 1/3 plus 5 and then dt. So I can make a nice table. And, when I make a table, let's see what happens as x goes to infinity. So we punch in 10, 100, and it's now the value of the integral is 11, 1,000 it's 82, 10,000 it's 498, 2,710 when it's 100,000. So it looks like, that value is getting pretty large. This is 1.4, times 10 to the sixth, 1.4 million. So yeah, it looks like this integral is definitely diverging. from the table. Now, if you wanted to do it by hand, that's fine. But again, I'm just trying to, they're not asking me for values here. They're just asking me, does this thing converge? Does this thing diverge? And again, since the smaller function is diverging, we know the larger one, the original one, will diverge as well by the comparison test. Great. Okay, so another one. All right, so now this one, little different, but, you know, again, I'll start off, they're asking us to compare this integral to this one, and it's, we're on the interval from 1 to infinity for x is greater than or equal to 1. And yeah, let's do that. And now I just want to determine first off. Now, of course, we could look at a graph in Desmos, look at a graph and see which one's larger. But I'll just show you how we could do that by hand here. And then when I actually go to do the integral, I'll just punch it in because I know I know this one converges. I'm just telling you that right now. Anyway, so back to the paper. We got the integral from 1 to infinity of, the original is this 3 over, 4x to the fourth plus 5, 4x to the fourth plus 5 dx. And we're asked to compare to the integral from 1 to infinity of just 1 over x to the fourth. Now, we're on this interval where x is greater than or equal to 1, right? So the original, 3 over 4x to the fourth plus 5, this 5 is positive, right? If I get rid of that, that'll make the denominator smaller. Everything's positive, actually, because you got, positive numbers raised to, positive powers and all that, blah, blah, blah. This is all positive. When I get rid of the 5 in the denominator, that'll make the denominator smaller. Now, if you make the denominator smaller, you actually make the number bigger. So this will be less than or equal to 3 over 4x to the fourth. Sorry. And then this is 3/4, times 1 over x to the fourth. This is the same thing as 3/4 times 1 over x to the fourth. But 3/4 is less than 1, so this will be smaller than 1 times 1 over x to the fourth, right? So this time, what we're comparing to is the larger one. So I'm going to call that g. Right? We're calling the larger function g all the time here, and the one we were starting with was the smaller one. Right? So again, here's g, if g is on top, f's on bottom. Now if I do this integral here, integral from 1 to infinity of 1 over x to the fourth, if the larger, that's his larger area, right? If that converges, then the smaller one has got to converge as well. If it diverges, I can't say anything about the smaller one, right? So if this converges, we know the smaller one does, the original one does. If this diverges, we can't say anything, right? We'll just go inconclusive. Now I'm going to tell you, I already know this converges, but just to double check, all right, I'll just show you. I mean, I know you could easily do that. That's a power function. You could easily just use the power rule there. But if I enter this real quick in my calculator, right, integral from 1 to infinity of 1 over x to the fourth, I'll just do x to the negative fourth dx. You see it's approaching a third, 1/3, okay? It's actually perfectly a third if you change it to a fraction. So this converges. And again, if this function here, this 1 over x to the fourth, that was the larger one. And if that converges, right, the smaller one's going to converge as well. So I'm selecting converges for our original integral by the comparison test. Great. All right. Okay, and again, we're asked to compare this to this. All right, so this time I'm going to show you on Desmos here. We'll enter these functions. Sine squared of x plus 1 divided by x squared plus 4, and then 2 over x squared plus 4. The larger one's going to be 2 over x squared plus 4 because, remember sine is always less than or equal to 1. So this numerator is always less than or equal to 2. So the larger one is the one 2 over x squared plus 4. But let's see that. All right, let's see that. And we're on the interval, right? We're on the interval from 0 to infinity. So I'm just going to look at for x values greater than 0. All right, so again, the larger one is going to be that 2 over x squared plus 4. And the smaller one will be what we start, the integral we started with. The integrand was, sine squared x plus 1 divided by x squared plus 4. All right, and you see they are equal at one point, but the green graph is, 2 over x squared plus 4. The purple graph is sine squared x plus 1 over x squared plus 4. And then, from 0 to the right, the green graph is always as high or higher than the purple graph, right? They do hit on occasion, right? They do touch each other on occasion, but the green graph is always at least as tall as the purple graph, all right? So if I took the area under the purple graph, uh, under the green graph, we're doing this integral from 0 to infinity of, g of x. And that looks like pi over 2, actually. This converges. And that was the larger function, right? That's this one up here, all right? The green one, 2 over x squared plus 4. So the area under the larger one converges, meaning the area under the smaller one must also converge, right? By the comparison test. So I'm putting converges. Great. Should have just one more of these. All right, and that's another one that's real nice where they give us a picture again. All right, so here we have f is 1 over x squared. Looks like that's the middle function, right? See the function in the middle of the inequality here. On the interval from 3 to infinity, right? So from 3 onward, f is in between g and h. G is the 7 over x squared plus 2. H is e to the negative x. And they're telling us that this integral from 3 to infinity of 1 over x squared converges. Now that's the middle function. All right, the integral under f, the area under f from 3 onward converges. So if the integral under f converges, h is smaller than that. So by the comparison test, we know that the integral, the area under h must also converge. All right, so that's this option. And that's it, because g is bigger than f, right? The area under f converges. But anything bigger than that, you couldn't tell anything, right? There was that was an inconclusion. You couldn't make a conclusion out of that from that test. So if the area under f converges, only smaller functions we would guarantee convergence. Anything larger, you'd have to do some other check or actually do the integral. So the only thing we can state out of this by using the comparison test is that the integral under the smaller function converges. The integral from 3 to infinity of h converges. And that's it. Great. All right, so again, hopefully this comparison theorem made sense and was easy to apply. All right, and oh, there is one more. I thought that should be the last one. I thought based on the progress here. Okay, well, again, we get this integral compared to this integral. This function, the 2 over 4 squared root of x plus 3, that will be smaller than 1 over the square root of x. All right. And let me just show that to you, and I'll put those two functions up. And we're looking on the interval from 9 to infinity, right? So let me go out here to x equals 9 on the horizontal axis. Now that original function, I know it's going to be smaller, so I'm going to call it f was, 2 over, what was it? 2 over 4 times the square root of x plus 3. Or square root of x plus 3. All right, so there's the red graph. And then I know the other one's going to be larger. G of x equals just 1 over the square root of x. See, it's larger. And this integral is a lot easier to take, the integral from 9 to infinity of 1 over the square root of x. So let's do that integral. Now, since it's the larger one, if it converges, we know the smaller one converges, right? We'll know the original converges. If it diverges, we can't say anything about the smaller one. You don't know, right? So let's take this integral under the larger one, under the blue graph, under g, 1 over the square root of x. Integral from 9 to infinity of, g of x dx. Right? Now it says undefined. Again, that does not mean it's divergent. It more than likely does. All right, now this is also an easy integral to take. I mean, you could easily do this with the limit. But again, I'll show you with a table here. I'm going to change this to x, change my variables in here to t, and we'll be able to set up a table for this. And I'm going to plug in larger and larger values of x, right, from 9 to infinity. So 9 to 10, that's not that big. 100, get an area integral of 14. 1,000 is 57. And 194, 626, 1994, 6,000, 19, blah, 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 blah. It's getting gigantic, right? So definitely blowing up. So my integral, all right, the area under the blue curve, let's get rid of this. So the area under my blue curve, under g, under 1 over the square root of x, is getting huge. Remember, that doesn't tell me anything about the smaller one, under f, under the red curve. That could be small enough to be convergent, but it could also be close enough to the blue one to be divergent. I don't know. So in this case, we have an inconclusive comparison. Right? Just because, I know the area under the larger curve is infinite, right? Divergent. Doesn't tell me anything about the smaller function. Okay, inconclusive. All right, and so that should be the final one, I'm hoping. Oh my goodness. They really are. All right, well, this one is actually very similar to one we just saw with, there was a few examples ago with sine squared plus 3. Sine is always less than or equal to 1. So this function here is always going to be less than or equal to 4 over, 1 plus 3, 4 over the square root of x plus 5. So I'm just going to say this one. All right, I know this. I can see this because, again, it's very, very, very similar to what we just saw a few examples ago. So the smaller function is the original. The larger function from 0 to infinity is the new one, all right, the one we're comparing to. Now this integral under the larger function, 4 over the square root of x plus 5, that's going to be divergent. This is very much like 1 over the square root of x, very similar. And we just saw in the previous example that the integral of 1 over the square root of x, from 9 to infinity was divergent. This is 0 to infinity. It's also going to be divergent. So this is divergent. And again, if the larger one is divergent, you can't say anything about the smaller one. So once again, I have an inconclusive comparison test. And again, you can go through this and see that this is divergent, but like I said, this is so similar to previous problems, I'm going to say this one. Save some time. All right. I know I said this the last two problems, but hopefully this is the last one. I can't believe this. All right, one more. Once again, this is incredibly similar to something we saw before. But this time, we have this natural log of x, so we're going from 1 to infinity. The natural log of x plus 2, this is going to be greater than 1. Oh, you got this 3 down here. All right, let me actually enter these. I'm pretty sure I'm pretty sure this first one is going to be larger, the larger function. All right, well, let's just double check. I could, do it by hand, but like I said, I'm pretty sure that one we start with is, I'm going to call it g because I feel like it's going to be the larger one. Natural log of x plus 2 divided by, and then we had the cube root, right? X to the 1/3 power plus 5. I think was there a 3? Yeah, there was a 3 as a coefficient there. So 3 here. All right, and we're going from 1 to infinity. Right, so looking at 1 onward. All right, and then I think the smaller one's going to be the other one. All right, so that's equals just 1 over the cube root of x plus 5. Right, 1 over x to the 1/3 power, and then plus 5. Right, yeah. So this the one we started with was larger. This one's smaller, right? And we actually saw one like this earlier, right? The integral from 1 to infinity of this smaller function that we're supposed to be comparing to is actually divergent. All right, and again, I'll do the table thing where we go from 1 to x of f of t dt. All right, change some dummy variable. Get rid of the graph of that and then make a table, and we'll see that, as we plug in larger, 10, 100, 1,000, you see the value of the integral is getting larger and larger and larger and larger, right? Huge. So definitely divergent. All right, so again, the smaller one, right? The area under the blue one, the area under the smaller function was divergent. So that does tell me that the larger one must be divergent. Well, it's always larger. It's got to be bigger than a divergent, which is more divergent. I guess you could say more, just as divergent. But by the comparison test, this original integral must be divergent. Okay, there it is. All right, there it is. The objective is filled in. This is finally done. All right, great. So that's it for this assignment on improper integrals. So as I said at the top of the video, the questions I saw here may not be the exact same questions you see when you work on the assignment yourself, but I'm hoping, that the problems and the objectives are similar enough, that watching me do them here will help you in some way when you work on the assignment on your own. And thank you very much for watching.